Okay, so in a series circuit, we have a fairly simple relationship between the component resistors and the overall resistance of the circuit. We have a little bit more complicated situation if we've got a parallel circuit. So this is what a parallel circuit would look like. And remember, a parallel circuit is one where the electric current has a choice of what path to follow. So if we've got current coming out like this, call this I1, some of that current is going to go over that way. And maybe we'll call this I0. So some of the current will go over this resistor 2, and some of the current will come down over resistor 1. Right? So there's a branching path. Just like if you had a fork in a pipe for water, right? You have a split. So we just got finished talking about how if you go around a loop and you end up at the same point in a circuit, it shouldn't matter what path you took to get there. You should have the same voltage as when you started. So if we go starting at this green point, we go over the battery, we come around down over R1 and back around, we should be back at V0. And we should also be back at our original voltage if we go over the battery around the long way over resistor 2. Right? So no matter which path we took, we should be back at our original voltage because we're back at the same point in the circuit. What that tells us is like the only way that can be true is if the voltage that we lose going over resistor 1 is equal to the voltage we lose going over resistor 2. Right? So in the series case, it was the current that was the same, but you could lose different amounts of voltage. But here, it's the voltages that have to be the same, but we don't have to split the currents equally. So I1 R1 equals I2 R2 equals, right, whatever voltage change that is. Oh.
Can you explain that difference one more time?
Yeah, so the I did not mean to do that. Let me fix that. So the amount of voltage that we expend over going over R1 or going over R2, they have to be the same because we need to get back to our original voltage over here. So if we go around this first loop that includes R1, right? We have the rule that we derived on the last board, right? The sum of voltages around loop 1 should equal 0. But also the sum of voltages around loop 2 should be 0. So around loop 1, we get plus V from the battery, and we get minus I1 R1. That should be 0. So in other words, the voltage we gain from the battery should be equal to the voltage we lose by going over resistance 1. But if we go around loop 2, which includes resistor 2, so then we gain some voltage from the battery, we lose some voltage going over resistor 2, and when we add those together we should get 0. So in other words, the voltage that we get from the battery should be equal to the voltage that we lose going over resistor 2. Is that a little clearer?
Yeah, it is. Thank you.
Okay, excellent. All right. Give me a moment. I lost my train of thought. It's okay. That's okay. Yes. So I was about to say something about the currents. So we have a statement about the voltages around a loop. We also can make a conservation statement about the current at a junction. So for example, right here, we have this junction where we have one current coming in and two currents going out. Well, the amount of current coming out has to equal the amount of current going in, right? Those charges have to come from somewhere, right? And so that's the idea behind this junction rule. So if currents are going in, we'll call those positive, and if they are coming out, we'll call those negative. So in other words, the amount of current that comes in has to equal the amount of current that comes out. These two relationships that I've circled here, those are what are frequently called Kirchhoff's laws. So yeah, that's why they're going to be super useful in calculating things about circuits. But you can see where I think that maybe the term law is a little bit highfalutin for so simple a relationship. Okay. So with this last relationship, the one that the arrow is pointing to, I want to also remember Ohm's law, right? So V equals IR. And I would like to take each of these statements about currents and use Ohm's law to replace it with a statement about voltages and resistances. Right, so the current can be written as the ratio of voltage to resistance. And so we can rewrite this statement as saying the overall voltage divided by the equivalent resistance is equal to, so I1 would be the voltage over resistor 1 divided by the resistance of 1, and then I2 we could write as the voltage lost over resistor 2 divided by the resistance of resistor 2. and then we make note like, hey, this work we did over here in green said that actually V0, V1, V2, they all have the same magnitude. And yeah, that's true, they do. So we can cancel a V out of every term. So for parallel circuits, we have this relationship here. So the reciprocal of the equivalent resistance is equal to the sum of the reciprocal of the individual resistances. I know that may seem a little abstract, so let's toss in some numbers here, right? So if R1 was, say, a 1,000 ohm resistor, and R2 was a 10,000 ohm resistor, right? What's the equivalent resistance of this whole circuit? Well, we'd have 1 over the equivalent resistance equals 1 over 1,000 plus 1 over 10,000. Right, 1,000, we could also write that as 0.001, and 10,000 would be 0.0001. Right, so the equivalent, the 1 over the equivalent resistance would be, what, 11 10,000ths? So we take the reciprocal of both sides, and the equivalent resistance is going to be, instead of 11 10,000ths, it's going to be 10,000 over 11, which is going to be something like somewhere around 9,000 ohms. Questions or comments? Nothing? How did you get 10,000 over 11? I guess 0.0011 is the same as 11 over 10,000. So reciprocal of that is 10,000 over 11. Okay.
Okay, so obviously 10,000 minus 1,000 is 9,000. If you took the reciprocal of all of them to begin with, then wouldn't we end up with 10,000 minus 1,000?
And then you're saying, but taking the reciprocal doesn't distribute over addition.
If you multiply by by negative 1, is it?
So it's not multiplying by negative 1, it's to the negative 1 power.
Right, okay. So is it just coincidence that it worked out that way?
Yes, this one's just coincidence. So maybe, to illustrate, maybe let's use a different set of numbers. What if R1 is 3 and R2 is 4? So then we have 1 over RE equals a third plus a fourth. So a third is like 0.33 and a fourth is like 0.25. So this is going to be like 0.55. No,
Yeah.
0.58.
58, yeah.
So that's 0.58 is the same as 58 divided by 100. So we take the reciprocal.
Divided by 100.
Yeah, so we get 100 over 58. So a little less than 2.
Okay. All right.
That's a good question, though.
So if we have 10,000 over 11, how did you get ASL?
I'm sorry, Dolan, I can't quite hear you.
Sorry. So if we have 10,000 over 11, how do we get 9 KSL? I would have thought it would have been like 11 KSL.
So where did I put my calculator? And that's not SL. This symbol here, by the way, is capital Omega.
That's an omega, okay.
Yeah. So yeah, 10,000 divided by 11 is
909.
909.
yeah. Sorry, I was off by so not 1,000, 100. My bad. Good catch, though. Okay, 900. Thank you for the correction. That's what I get for just shooting it off in my head.
I was so confused. But thank you.
All right, so that's resistors. And we're going to come back to resistors in a second. But before we do, I want to talk about capacitors as circuit elements. So resistors and capacitors are two of the most common circuit elements. They're not, so capacitors, resistors. Later we'll talk about inductors, and then the big one that and then we won't talk about transistors in this class. It's a little out of scope. But those four things, resistors, capacitors, inductors, and transistors, make up all of modern electronics. So we talked about capacitors as being ways to separate charge. In circuitry senses, they're actually like ways of storing energy. Right? So you can get energy from a battery. You can also get it from a capacitor, right? So the capacitor has charge on its plates, and if we need to, we can bleed that charge off the capacitor and run it into the circuit to get current. So let's look at a circuit that has capacitors in it. We're going to start by what if we have two capacitors in series? So we're going to recall from last week that our definition of capacitance is the ratio between voltage and charge. So right, how much charge can you get on either plate of the capacitor by applying a given voltage? All right. So let's see. How do I want to talk about this? So the Kirchhoff's laws, laws that we derived on the last couple of pages, again say that if we look at the voltages around a loop, they should all add up to 0. Right? So we have some positive voltage here from the battery, and then we've got some voltage that we lose across the capacitors. Right, so the idea here is that if this long line here is the positive part of the battery, then this first capacitor, to balance it, it will collect negative charge here, which means that the other side of the capacitor will be positive. But to balance that positive charge, this capacitor will have a negative charge here, a positive charge here, and then the battery itself has a positive and negative end. So you'll notice that the voltages from the capacitor are kind of oriented the opposite way. Or no, sorry. Let's back that up, reverse it. The voltage from the battery is what causes the capacitors to bias, to separate charge. And so we use up some of that voltage to separate charge over capacitor 1, and we use up some of the voltage to separate charge over capacitor 2. By considering the loop, we can see that the amount of voltage we get from the battery should equal the amount of voltage we spend on the capacitors. If we replace the voltage with something in terms of capacitance, with using our definition of capacitance, we can play the same game that we did using resistances on the last page. Now, the charges that are on that are separated on each capacitor plate, they have to be equal, right? So the amount of charge separated here has to be equal to the amount of negative charge that is gathered on the first plate of capacitor 2, because we need there to be net neutrality throughout the system. So if these weren't equal, what it would mean is that we would still have a flow of electrons, right? If they weren't equal, then some electrons would flow either, if we had more positive charge on, so if we had more positive charge on capacitor 1 than we had positive charge on the second plate of capacitor 2, then we would see some flow of electrons going that way to neutralize it. And if we needed to flow the other way to get it to equalize out, we could do that. We would do that too. So when we were considering resistors in parallel needed to have the same voltage drop across each of them. Where here, what we need to be the same to get a stable circuit is we need the charges separated across each each circuit element to be the same. So we need, Q to be equal to Q1 to be equal to Q2.
And Q equals charge?
Yeah, where Q is charge. There is a loosely followed tradition where you use capital Q for charge on circuit components. Because they're, but then you use little q for like point charges. With the, and again, this is just a tradition, just explaining why I use those variables. The idea is that the big Q charge in circuits is composed of many little q point charges. So yeah. But yeah, little q or big Q, they both mean charge in this context. So we get a relationship between capacitances in series that looks exactly like our relationship for resistors in parallel. Does anyone want to guess what we're going to end up with if we consider capacitors in parallel?
We'll add them.
Yeah. Capacitors in parallel will look like resistors in series. And for much the same reason. So in parallel, so in parallel, we're doing some charge separation work from the battery, right? And then some of that charge gets deposited on the first capacitor. Some of that charge gets deposited on the second capacitor. So we're not, so in parallel, we're not conserving the charge, we're splitting it. So the total amount of charge we separate, right? Some of that goes on capacitor 1, some of it goes on capacitor 2. So if we want to play the same game and we replace these expressions for charges with something that has to do with capacitance, we can say, well, Q equals CV. So CV, total is going to equal C1 V1 plus C2 V2. And for the same reasons as when we considered the voltage in parallel resistors, we know that the voltage across parallel elements has to be the same, right? So if we have a certain voltage difference across the battery, that's going to be the same as the voltage difference across this parallel element and this parallel element, because no matter what path we take, we need to get back to our original voltage at, say, this arbitrary corner here. Right, so the voltage across the battery, right, is the voltage across the first capacitor, is the voltage across the second capacitor. All right, so far so good. Comments, questions?
Sorry, I think I might have missed it. So what is the purpose of a capacitor?
So the purpose of of a capacitor is to store charge that we can, use for current later.
Okay, thank you.
Let's summarize. So the things we know about circuits. We know that there are two kinds of circuits, and we know about two kinds of circuit elements so far. So things can be wired up in either series or they can be wired up in parallel. And we know about resistors, and we know about capacitors. In series, the equivalent resistance of two resistors is just the sum of those resistances. And in parallel, the equivalent capacitance is just the sum of those capacitance. Whereas parallel resistors, you get the reciprocal if you add the reciprocals. And you get something very similar for capacitors in series. So let's do a fun problem, right? Because these relationships actually open up a couple of pretty fun problem types. So let's say we have a circuit which is a little bit complicated. Okay. What is the equivalent resistance of this whole circuit? So this is a multi-stepper. Because obviously, like this circuit's a mess. Whoever designed this should be fired. But we can still analyze it in a theoretical sense. So there's both series and parallel relationships in this circuit. But we want to try and work with only 2 resistors at a time. Right? So let's start with R5 and R6. Are R5 and R6, are they in series or parallel?
Series.
For sure. So we can maybe say R5, 6, which is the equivalent resistance of 5 and 6 together. Right? Because they're in series, we can just add them. Okay. So when we say that we have an equivalent resistor, we mean that drawing the circuit diagram like we did in blue and drawing it like we did in orange, those are actually the same circuit as far as any behavior of that circuit is concerned. So whether we have a 5 and a 3 ohm resistor next to each other in series or a single 8 ohm resistor, makes no difference. So for all purposes, this blue and this orange circuit are the same circuit. So what can we attack next?
We do R1, R2, and R3.
Well, R1, R2, and R3 are in series with each other if we didn't have 4 and 5, 6 out to the right.
R3 and R4 then.
And how are R3 and R4 related?
3, 4, and 6 all at the same time, though?
Yeah, we could totally do that because these 3 here are all in parallel with one another.
Yeah.
So if they are in parallel, then we have to do reciprocals. And because I don't want to write 3, 4, 5, 6 as a subscript, I'm just going to call that RA.
0.25 plus 0.5 plus 0.333.
You are right on it, Liz.
Yeah, except she didn't hear the first point, so it didn't work. I'll do it again, but I'll mute so everyone doesn't have to listen to me talk to Siri.
So R3 is 4, so 1 over R3 is a quarter. R4 is 2, so 1 over R4 is a half. And R5, 6 is 8, so 1 over that is 0.125, an eighth. Right, so 1 over, 275, yeah, 875. So 1 over is like 0.7875. Right? Unless, wait, a fourth plus a half plus an eighth. That should be 7/8. Yeah, 0.875.
I got 0.875.
Okay. So that's 7/8. So if when we take the reciprocal, it should be 8/7 of an ohm. All right. And now we're down to a simple series circuit. So our total equivalent resistance is R1 plus RA plus R2. So 3 plus 2 is 5 plus 8/7. So is that 43/7? Questions, comments? All right, everybody good? All right. So I like these. They're little puzzles that are kind of fun to unpack. So let's look at another circuit. And again, we're going to look at a circuit with just resistors for now. Okay. So here, say this R1 is 10, R2 is 5, R3 is 20, and we're running this whole circuit off of a 4-volt power supply. So my question here what currents should we expect to see at various points in the circuit? Right, so what are I1, I2, I3? Our currents. Does anyone have an idea of how to start? I'll give you a hint. We just did it on the last page. Yeah. So the very first thing that we might try to do is to write down a single equivalent resistor for this whole thing. Because I1 here, this first current, the current over the equivalent resistor for the whole circuit, that's going to be I1. So if we want to add the reciprocals here, it's going to, so 1/5 plus 1/20th, and then the reciprocal of that. So a fifth is 0.2, a 20th is 0.05. So add them together, we get 0.25. Take the reciprocal, we get 4. And then the equivalent resistor for the whole thing. So now we've got this 10 ohm resistor that's in series with this equivalent 4 ohm resistor. And since they're in series, we can just add them. So the resistance for the whole thing is going to be like 14. Hanson asks, can you repeat again how you got 4? Yeah. So let's see. The I mean, there are a couple of ways you can think about adding these fractions in here. I mean, of course, you could just pull out a calculator, but if you don't have a calculator, maybe get a common denominator here. So 1/5 is the same as 4/20ths, right? So we have 4/20ths plus 1/20th is 5/20ths inside there. And then when you take the reciprocal of 5/20ths, you get 20 over 5, which is 4. All right. And then when you add it to the 10 ohm resistor up here, it gives you a total of 14 for the whole circuit. So that lets us say, well, then the current that's coming out of the battery, right, times the resistance for the whole circuit has got to be equal to the voltage for the whole circuit. So we have 14 I1 equals 4. And 4 over 14 is like, what, 0.29? Okay. So that gives us one of the currents. What are we going to do for the others? For the other two? So here we can pull Kirchhoff's rules here. So if we analyze this this junction here where the three currents meet, so the sum of all currents going into or out of a junction has to be 0. So we know how much is coming in, 0.29 amps. And then I2 and I3 are coming out. So if we can find either I2 or I3, this gives us a way to find the other one. And the other piece of information we're going to use, I mean, we have some choices, but I would say probably our best bet is to use the other Kirchhoff rule, right? So the sum of voltages around a loop should also be 0. And we can pick whichever loop we want. So for our purposes here, I'm going to choose the loop that starts at the battery, goes around, goes over I1, or goes over, sorry, use I1, goes over R1, and then I2 over R2, and then back to the battery. So we're going the, quote-unquote right way over the battery, right, from negative to positive. So that's going to give us a positive voltage and voltage increase. Then we go the right way over the resistor and the right way over the second resistor. When I say right way and wrong way, what I mean is we have to make some initial guess as to which direction the current is flowing. So when I drew this picture, I kind of made a guess that the current was flowing clockwise. So if a current, if we're traveling with the current over a resistor, we're going to lose voltage. If we decided to run our loop the other way, right, instead of running it clockwise like I chose here, what if you went counterclockwise around the loop? Well, then you would go the wrong way, quote-unquote wrong way, over the voltage source, which means you would get a -4, and you would go the wrong way over the resistors, which means instead of losing voltage, you'd gain voltage. Basically, it would have the effect of multiplying this whole equation by -1, which isn't going to change the results of that you get at the end. Anyway, so you make an initial guess as to the direction. If we end up solving this whole thing and we get a negative value for I2, that means we guessed wrong. And that's fine. We just guessed wrong. It happens. And so in which case we know that I2 doesn't actually flow from top to bottom. It flows from bottom to top. So we gain 4 volts going over our battery. We lose voltage going over the first resistor in the amount of I1R1. We lose voltage going over the second resistor in the amount of I2R2. And both of these are consequences of Ohm's law, right, where V equals IR. And conveniently, in this blue-gray equation at the bottom, the only thing we don't know is I2. We know everything else. So I2 is equal to 4 minus I1R1 all over R2. That's going to be 4 minus 0.29 times 10. All of that divided by 5. So then we can take this, come back to our previous equation, and find then that I3 has got to be equal to 0.07. Right? Because if we've got 0.29 amps of current going into the junction, and we've got 0.22 leaving the junction over R2, that only leaves 0.07 amps of current to go over R3.
There, we should be able to subtract the 0.29 from 0.22, add them, switch that to the other side, and we should have I3.
That's right. So it looks like the large majority of the current is going to go over R2 rather than R3, which makes sense because R2 has a resistance of 5 ohms, R3 has a resistance of 20 ohms, and for the most part, electricity likes to take the path of least resistance.
For the part where it says I2 equals the 4, that's supposed to be R1 in the numerator.
Oh, good catch. Yes.
Okay, because I got confused for a second.
Yeah, my bad. All right, so in the second half of class today, we covered 21.1.2.3, 21.6, and 19.6. The other sections in chapter 21 and 20 are interesting. So 20.6, 20.7 are interesting. And you should read them, but I won't be choosing problems from them. Same thing of 21.4 and 21.5. They're interesting, and your labs will be dealing with them, but I won't be quizzing on them in class.
Sorry, can you repeat those?
Yeah. So the sections which we have not covered in class and won't cover in class are 20.6, 20.7, 21.4, 21.5. So those sections we're not going to cover here. You should read them because they're interesting, though, and your lab will deal with them.
Baby?
Is it baby time?
For me, it's almost always baby time.
All right, so I think that's actually it for today. We got done a smidge faster than I expected. That's all the material that I had planned on presenting today. If you have questions you want to ask, feel free to stick around. If you want to look at Dolan's baby, feel free to stick around. Otherwise, have a great weekend. And, I hope you all saw the announcement. The winning office hours time was Thursday at 10 a.m. So if you have questions on things that you encounter in homework, please come to office hours and we'll chat about it.
You're going to go over the
Oh.
quiz too, correct?
Thank you for the reminder, Alyssa. we are totally going to go over the quiz. Which slide was that on? Oh, yeah, there it is. Okay. 2-point charges exert a 5 Newton force on each other. What will the force become if the distance between them is increased by a factor of 3? So we want to pull out Coulomb's law. Right? So the force that 2-point charges will experience is equal to K Q1 Q2 over R squared. So at the first amount of separation, they exert a force of 5 newtons on each other. So what happens if we triple the distance between them? Right, so if we expand this square on the bottom, not K1, just K. And then we make the identification that all of this stuff here, that is F1. So F2 is in fact F1 over 9. So if you triple the distance, you only exert 1/9 of the force.
Would it be okay if we plugged that in? Because I did 5 over 9 and then got 0.56.
Yeah, I mean, you could totally say this is 5/9.
Okay.
For sure. All right, so that's question 1. Question 2 asks us about the electric potential of a point charge. So the voltage of a point charge is equal to K Q over R. So if we want to look for the distance at which it will be a certain value, we can totally solve for R. So R is equal to KQ over V. So the first, when we're dealing with 100 volts, we can do a plug and chug from here. So K is 9 times 10 to the 9. The charge is 1 microcoulomb, so that's 10 to the minus 6 coulombs. And then we have 100 volts in the denominator, so that's 10 to the 2. So we've got, the only thing that's not a power of 10 is this 9. So we have a 9 times 10 to the, and we have positive 9 in the numerator and a negative 6. So that leaves us with a positive 3 overall, and then divided by 10 to the 2 in the denominator. That leaves us just 10 to the 1. And of course, if we're using SI units here, this is going to be 90 meters. The second distance, very similar. They are just trying to catch you up with scientific notation. But it's, 2 times 10 to the 2, that's 200. So at 100 volts, you'll get 100 volts at 90 meters. So if you want twice as much voltage, you have to go to half the distance. Questions or comments?
Did you get 10 to the negative 6?
It's 10 to the negative 6 is the power for micro. Right, so that little mu means micro. So 1 microcoulomb is 10 to the minus 6 coulombs.